So this chapter is about multi-dimensional scaling, MDS, multi-dimensional scaling. And it's also a dimension reduction method, like PCA is and like CCA, canonical correlation analysis is, but it takes a different approach to PCA. So in PCA, our starting point was a data matrix, X. So this, on each of our n observations, we had p different measurements. So you can think of this as a matrix of features or a matrix of covariates, different pieces of information, different measurements on each of your n covariants. And given X, we try to find some reduced dimensional variables Y that have approximately the same covariance matrix as X, okay? Where the Y's now lie in a lower dimensional space. So we didn't think about it this way, but we're trying to match the covariance matrices in some ways. Okay, so we're trying to find a Y such that Y transpose Y is approximately equal to X transposed X, which was NS. So the starting point in MDS, in multidimensional scaling, is different. We start with a matrix of similarities. Okay. So we start with a matrix D, which is an n by n matrix of distances or similarities between the n cases. So that's our starting point. It's not an n by p matrix, it's an n by n matrix. We don't have the features, all we have is distances. Okay, so we try to find a set of points y1 up to yn, such that the distance between yi and yj is approximately dij. Okay. So we think of this distance matrix here as being the elements dij, I and j from 1 up to n, where dij is the distance between xi and xj. Okay, we often write MDS as an optimization problem. We're going to try and find y1 to yn such that the sum of the differences between dij and the distance between yi and yj is small. So let's say to minimize this. Okay, so we're going to sum here over I from 1 to n and j from 1 to n. And we'll talk about what these distances are later, but we don't need to specify the type of distance. Okay? We don't need to specify whether it's a distance or a dissimilarity or a similarity here. We've just got some measure of dissimilarity or similarity between the pairs of points. So to illustrate this, let's think about an example. Let's consider the location of England's cities, or some of England's cities. So on a map here, and we can have their location recorded by their latitude and their longitude, say. So London's obviously at 0 longitude. Now, given their location, it's fairly easy to go from their location to the distances between the cities. If you tell me their coordinates, I can look up how to compute the distance between them. And so that's what we have here. This is probably a bit small for you to read, but we've got the distance between each pair of cities. So we only need a lower triangular matrix here or an upper triangular one, okay, and that it's repeated information top and bottom. But for example, you've got the distance between London and London is 0 kilometers, whereas the distance between London and Birmingham is 163 kilometers. The distance between Manchester and Birmingham is 114 kilometers. So it's easy to go from the features, the x's, yeah, the data observations, to the distance matrix D. That's what this is, our distance matrix D. The aim in multidimensional scaling is to go the other way. We would consider being given this distance matrix D, and what we'd want to try and do is find a set of coordinates of points that have these distances between them. Yeah. So for n cities, we want to find a set of n points for which the distance between them, their distance matrix of these n points is D. And we're going to do this only starting with the distance matrix. So that's the aim of MDS. Instead of starting with data, we start with a distance matrix, and from a distance matrix, we want to find coordinates that have those distances. Whereas in principal component analysis, the aim was different. We started with the data matrix, and we tried to find a set of coordinates that had similar distances or similar covariances. So let's consider a distance matrix D, which is D11 down to dn1 across to d1n to dnn. So the distance between n objects. Now, if this is a distance matrix, there's various properties we want it to obey. First of all, we need all the distances to be bigger than 0. Now, we're not going to be dealing with negative distances here. We also want to specify that a distance between an object and itself is 0. The distance between object I and object I is 0. We're going to require the distance matrix to be symmetric. The distance between I and j has got to equal the distance between j and I. And then finally, we're going to want to know that if the distance between object I and object j is 0, then object I is the same as object j. Case I is the same as case j. So these are the axioms we're going to require for our distance matrix. So for those of you who have done some mathematics, sometimes we define something called metrics. So we're just going to say here we don't require distances to satisfy the triangle inequality. Okay, so the triangle equality says that the distance from I to k must be less than or equal to the distance from I to j and the distance from j to k. Yeah, so if you think about going between I and k, that distance has got to be less than the distance from I to j and j to k. Okay, so that's something we normally assume about distances. We don't require that here. We don't require this to be true. If it is true, so if D does satisfy the triangle inequality, it is a metric distance. Otherwise, it's a non-metric distance. Okay, so all reasonable distances in mathematics are metrics. Okay, but we're going to be dealing with sometimes with data that is the result of asking people to rank similarities or to say how similar different objects are, and people aren't always consistent. So suppose I was asked about the difference between certain restaurants. So I might say, well, there's a big difference between Pizza Express and McDonald's. But then you might also ask me the difference between Pizza Express and Pizza Hut, and I might say, well, yeah, there's some difference, but not that big. And then the distance between Pizza Hut and McDonald's, I might say, oh, it's not that big. And I might violate the triangle equality in my subjective distances. Okay, so data that derive from subjective opinions often don't satisfy this triangle inequality. So you've seen many choices of distance. So let's just have some examples. So you've seen Euclidean distance, or this is sometimes called L2 distance, or as the crow flies, the distance between x and another point x prime, and the L2 distance, Euclidean distance. Well, this is just x minus x prime transposed x minus x prime all square rooted. Or it's also equal to the sum of xi minus xi prime squared, all square rooted, I from 1 to p. Okay. We also saw the L1 distance, and this is often called the Manhattan distance. And I'll explain why it's called Manhattan in a moment. But this is the distance between x and x prime. This is just the sum of the absolute differences between the elements. Well, why is this called the crow flies distance or the Manhattan distance? Well, let's imagine we've got 2 points. So let's imagine we've got x up here and x prime down here. Well, Euclidean distance is just the shortest route between them. This is the Euclidean distance, whereas the Manhattan distance, or the L1 distance, measures this. Okay. So this is the Manhattan distance. Okay, and why is it called Manhattan? Well, it's because New York is arranged in blocks like this, and so it's the way a taxi would go, if you like, or a car would travel in New York. You have to go north, south, then you have to go east, west. Okay, and there are many other choices of distance, and we don't have to understand the distance or have it defined. We might just be given a distance matrix and not know where it's come from. It might not be defined mathematically. It might just be from asking people their opinion. So we're going to see some examples later and how the choice of distance can matter and make a difference. But the focus of this chapter, our focus, is going to be on Euclidean distance. And the reason we're going to focus on Euclidean distance is that it's only the Euclidean distance that allows us to solve the optimization problem we stated mathematically. Any other choice of distance, and we have to use numerical optimization, but we'll get to that later.